So let's go ahead and get started here. So for the agenda today, we're basically going to talk about the current and future requirements of faster overall data transfers, especially regarding long-haul transfers of transcontinental communication links that have not really changed in speed in the last 10 years or so. Then we'll investigate different methods being used to speed up the transfer rates and how we can make this more efficient as far as being able to design and engineer systems that can handle these different techniques. Then we'll get into coherent optical, what it is and how it's tested. So as we all know, optical networks have been around for some time, and we know that back in 2000 it was a very hot industry and everything was going optical. And then it was realized that the speeds of the networks and much more challenging the expensive capabilities as far as decoding and modulating these signals became much more of a challenge than a lot of engineers suspected. And so the speeds that they thought they could get out of the optical networks were not capable with the expensive types of technology that were available at that time. So a lot of the companies went to working on shorter distances and wired communications such as USB and PCI Express and some of the serial standards. But this doesn't help with the long-haul optical transcontinental data links that people are using today and want to be able to transfer these huge amounts of data. So new opportunities have arisen, and there's been a lot of research in this particular avenue of optical networks. So you can see here the need for speed is growing, and it's going to grow exponentially in the coming years. And this is a table from a Cisco evaluation of who's wanting faster data and where we're seeing the growth increases. Of course, we're seeing with the large population areas, seeing the most requirements for the change. A lot of this is in mobile data, but we're seeing that the IP data transfers is probably the most demanding because of the consumer area where people are transferring movies and large blocks of data, and also industries being able to communicate between their different countries in order to have efficient data communications. And so having the capability of transferring these big blocks of data over a continental transmission line is very important. So in the past, or actually up to today, the improvements that have been tried in order to increase the efficiency of optical communications. So we've looked at the improvements applied over time to optical signals, and the traditional method for modulation is on-off keying. This is basically what's used in many of the optical transmissions today. It's a very simple off-on type approach, but this doesn't offer any speed increases, and the only way to get speed increases in many cases is to add more fiber links, improve the characteristics of the fiber by doing different dispersion and attenuation techniques. And then being able to multiplex multiple signals into the fiber by assigning different wavelengths to them has been another area that a lot of people have been exploring and been using actually. But all of these techniques have not improved the data transfer rates substantially, as we will see here in future slides. So as bits are transferred faster and faster, optical signal drift away from the ideal conditions. And issues like bandwidth, both optical and electrical, and dispersion, especially chromatic dispersion, start to raise a wall of impending further improvements. Ultimately, the distance between contiguous wavelengths in the DWDM dense wavelength division multiplexing installation also limits the maximum baud rate, and individual wavelengths can be modulated. Otherwise, beyond some limit, each wavelength would interfere with the adjacent wavelength. And this is where we get into a lot of crosstalk and also cause higher bit error rates. Under these conditions, information is carried by a single optical parameter. Power and phase of the optical carrier is not typically important until its behavior affects the capability of the transmission. So we can see that in order to get to the high data rates that we're looking at, that most consumers want to have the capability of today, we have to go to some new techniques in order to accomplish that. So wireless and cable RF transmissions have been kind of a learning curve for not only wireless but optical, in the sense that different modulation techniques have given us the capability of increasing the spectral content and data transfer rates. So the different modulation schemes have been the biggest benefit of what we can do with these optical fibers that are already in place. And in fact, there's a lot of dark fiber out there that could be used if it was used efficiently. And in some cases, some new fiber will have to be placed in order to fulfill these requirements too. So common trends have been to use higher order modulation schemes. When more than one bit is transmitted during a simple period, the exploitation of different kinds of orthogonally, where multiple independent messages can be sent simultaneously over the same link. So this is the idea, is using several different modulation schemes in order to increase the efficiency. Then there's other methods that require that you phase shift the modulation schemes by 90 degrees, and this is where we get into using an IQ modulator in order to increase the efficiencies of the actual transmission capabilities. So if we look at a couple of the modulation schemes that are used today, we can see that OOK, or on-off keying, which was the key capability that many modulation schemes have been using for many years. Traditionally, you can get up to 10 gig transfer rates with this type of modulation. Again, this is where we're kind of locked in with the current types of modulation only allow us to go up to around the 10 gig capabilities. And then the phase shift keying also is a 1 bit per symbol modulation scheme. So in this case, we're not really improving any of the transfer rate capability with these specific types of modulation. QPSK has been another one that's been used quite efficiently for quite a while. And in this case, you can see that the more quadrature phase shifting that you can do gives you more symbols, or more bits per symbol. So this is another way of improving the efficiency of this modulation scheme. So there's also the dual polarization QPSK, and this gives us up to 4 bits per symbol. And this methodology is capable of, again, increasing the speed of somewhat, but still not up into the rates that people are expecting of being able to transfer at up to 30 gigabaud or up to 1.5 terabits of data transfers speeds. So if we look at some of the principles here applied to the frequency domain, OFDM, or orthogonal frequency domain multiplexing, requires the independent synchronous modulation of multiple carriers to be spaced exactly 1 baud rate hertz apart. In this way, it's possible to recover the modulation state of each individual carrier without experiencing any inter-carrier interference. So OFDM modulation can also be implemented through the application of an IQ-based system like we talked about earlier. Signals in the quadrature modulator, these baseband signals are obtained by mapping the modulation states to the individual carriers in the frequency domain and applying the complex IFT to the OFDM relatively narrow and simple duration correspondingly long capability. So again, OFDM has been one of the new types of modulation. I wouldn't say new, but it's one of the types of modulation that many people are using with coherent optical networks as they're doing this test research. So coherent optical has been on the drawing board for quite some time, but just in the last 5 years or so, it's been more of a research project than reality. Part of the problem is that simulations have been proven. Finding methods to actually provide the required modulation has been a challenge. It is important to test transceivers with real-type signals so the decoding can be verified and the transmission quality can be verified. So this is where the test equipment comes in the sense that you need something that can provide generation capability that gives you these modulation schemes in a clean spectral environment, and then check it through the fiber, either through a long-haul fiber or through the directly into the receiver, and verify that the receiver can decode these complex OFDM or QPSK type modulation schemes. Now, we talked about IQ as a basis for many of these communication links, and in some cases are also using polarization, and so 2 IQ channels are used in order to improve the efficiency. In this case, you see the generation side, many engineers have been using basically a pattern generator up to the 32 gigabit rate, allowing to do direct transfers or creation of these schemes. The problem with using the pattern generator is it doesn't give you a multi-level signal. And in order to create multi-level signals, then you have to add more complex circuitry after the pattern generator in order to create PAM-type signals or multiple modulation scheme-type signals. Now, on the other hand, there has been AWGs that have been used, arbitrary waveform generators, that have been used for this type of application, in the sense that they can create all the modulation schemes required. The only challenging part is most AWGs don't have the speed in order to give the engineer the capability of doing these data rates up to the 30 gigabaud rate. So within the last year or so, Tektronix has come out with a 50 gigasample AWG that supports up to 30 gigabaud transfer rates, and the only challenging part is in order to do the phase modulation with the polarization is that you need 4 channels, and so that would require stacking 4 AWGs up and and using 4 AWGs as your signal source. Many customers are using 2 AWGs and trying to do this without doing the polarization capability, or they actually go out and synchronize 4 AWGs, and that works fine. Then we get into the analyzation part, where first you need some sort of decoder or receiver that allows you to turn the electrical signals that come out of the arbitrary waveform generator or pattern generator into an optical signal, and then sent through the fiber, and then actually analyzed through a decoder on the other side, and then the measurement system of the analysis system does the specific measurements required for the optical network. So as you see here, basically what I mentioned in the last slide is that our engineers are using 2 AWGs, and in many cases they can connect the AWGs directly up to the analyzing system to verify the open eye, see what it looks like before you send it through the transmitter or the receiver and the transmitter or the transceiver circuitry. And this gives you an ideal condition, and then what you do is you actually connect it to the transceiver and then look at the output of the transceiver with the analysis tools and verify that what kind of loss you get, how close the eyes are, what your EVM characteristics are. So you have a lot of flexibility as far as actually generation of these signals so that you can test them appropriately and make sure that your transceiver is indeed working properly. So as we look at some of the more challenging modulation schemes, you can see that in many cases people are going to QAM type signals. QAM 16 is a preferred methodology, either with a QPSK signal or an OFDM. And this gives you the capability of more data bits more data bits per symbol. So this is a challenge for a pattern generator in the sense that it's very difficult to build these QAM type signals with a pattern generator, whereas the AWG can support up to 16 QAM no problem. With the sample rate and record length that's available today, we have no problem being able to build these type of modulation signals that then can be used for the actual testing. So as you see here, the AWG with its RF capability of up to 20 gigahertz bandwidth or frequency response, analog bandwidth up to 15 gigahertz, gives us the capability of the 30 gigabaud. Basically, to calculate the requirement for the bandwidth is to take the baud rate and divide it by 2, and this will give you the requirement for the analog bandwidth of the generation capability. So the new DAC system and AWG characteristics of the 70,000 series from Tektronix gives these engineers the capability of creating these signals. Like I said, you can see PAM16 on the right there, and then you can also see on the top right the spectral content of the AWG, and this is one of the important, somewhat important parts, is how clean the actual output is, and this is basically looking at the spurious free dynamic range of the AWG, which in this case can be as low as minus 80 dBc. We've had lots of research being used to create these optical signals, and you can see a quote down below from Bell Labs that basically with the 50 gigasample capability, they were able to transfer the 30 gigabaud rates, and they were actually able to get up to the 1.5 terabit data transfers that people are looking for as far as an efficient long haul transfer. So in order to get the clean, efficient modulations from the AWG at the speeds required, in many cases the digital to analog converters that are used today have to be interleaved in order to create the faster sample rates. In this case, with the Tektronix AWG, we use two 25 gigasample DACs that are interleaved in order to get to our 50 gigasample sample rate. And not only does the interleave give us the capability of higher sample rate, but it does improve the frequency response too, because we're going out past Nyquist with the higher sample rate. So in this case, having an interleave box does actually add efficiency to being able to create these signals at the data rates required. You would think that interleaving would actually be an imperative, but in this case it really isn't, as long as it's done correctly. So as I mentioned before, the AWG has the capability of creating or generating lots of different types of modulation schemes. And these different techniques allow engineers to test different modulation schemes in order to determine which one is going to work best for their spectral efficiencies over the long hauls that we're trying to get the best data transfers with. And so we can emulate not only the perfect type of modulation scheme, but we can add impairments to these, so then we can test the receiver to see what's going to happen if your system is a little bit noisier than expected on the transmitter side. And so the AWG can simulate even a long haul transfer such that you don't have to actually connect it through the long haul. You can test it in your lab, your receiver, such that it simulates basically what it would look like coming from a long haul transmission. As I mentioned before, some of the techniques that are being used is to use polarization in order to get more efficiency. So engineers have been looking at complete polarizing division multiplex transmitter, and in this case, again, it's very challenging in order to do this test, because you do need two IQ-based generation capability in order to provide the capability of doing the interphase modulation. And so, but again, this is just another technique that's being used, and I think most people or most engineers will go to when they actually build their devices, they test it with maybe not using the polarization, and then they build their actual transmitter with the polarization capability. They can prove it with that it works without the polarization, then at least they can verify that the receiver can do the decoding correctly and all the requirements in order to do that. So we can also do a single channel capability where you use the positive and negative output of the differential pair to create the IQ effect. So what you can do is you can put a delay line, a 90-degree delay line, or some sort of phase delay in one of the outputs, and this acts as if it's a IQ channel rather than just a differential channel. So in many cases, if it's a cost-effective methodology, they can use one AWG, and with a little bit extra circuitry on the exterior, you have the capability of testing these systems up to the data rate that you want to test at. So this is just another method that engineers have been using in order to verify that their system's working properly. So on the analyzation side, the requirements here are pretty straightforward in the sense that in order to optimize the networks and the advanced modulations that we're using, we need to be able to measure the actual optical constellation parameters and the quadrature, leakage, things like that, that could affect the overall transmission quality. So having the capability of the generation and the analysis allows engineers to verify their simulations are actually appropriate, and then we can put it into a system that's a real-time system in the sense that it acts, the test equipment acts as real-world condition, such that you can verify that in the real world you're going to get noise, you're going to get channel effects, you're going to get other qualities that you don't really want, but you need to make sure that your receiver can handle them. The other things, of course, to look at the analyzer is to give the capability for manufacturing to enable automated testing and doing other things that require that once you've determined how the system's going to work, you have a methodology to verify that it's working with every component that you build. So, of course, you have to have some sort of analyzing tool. So, Tektronix also offers a Coherent lightwave signal analyzer that allows you to do this analyzation and do the measurements required for these particular techniques that are being used. So we see that in this case, basically you go through the capability of doing the phase polarization capability, and then come back out with an analog to digital converter that then goes into the processor that does the analysis itself, the measurements, and then out to a display so that you can see the eye patterns and the eye closures and some of the measurements that are required for these particular tests. And of course you can then log this data such that you can give it as a report or whatever in order to show your techniques are working or they're not working, whatever, for your engineering testing. So here we see a complete system again. This is with the OM 5110 and the OM 4106D, and it's paired with an oscilloscope in order to get the analysis displayed. And the software runs can run on the scope, but it can also run on a PC. And but the software basically does all the connections in order to tell the scope what to do, how to make the measurements. And we have the capability of doing this analysis on a real-time scope, and we recommend up to a 33 gigahertz scope, or you can do it on a sampling scope. We have both methodologies capable with this system. So this gives us the capability of doing complete analysis. The sampling scope was going to give you a little bit more dynamic range. There's more bits available. The real-time scope is going to be more, like the name says, it's going to be more of a real-time effect, so you don't have to wait as long for the processing, and you also have longer record length capability and higher sample rates. So I moved through this pretty quickly, but in conclusion, the the optical networks that we're working with today, we see a lot of promise, and being able to use test generators such as the AWG 70,000 series to do these coherent optical tests has been proven to be one of the best applications for this type of product, in the sense that it really gives the opportunity for engineers to do this testing appropriately. And so some of the things that that you need to look at if you are looking at using an AWG is, of course, we talked about the number of channels in order to do either IQ or polarization. Sampling rate, basically you need, in order to create 30 gigabaud, you need sample rate that can give you frequency responses up to the 15 gigahertz or higher. And then that also correlates with the bandwidth. Record length is also important. You can build some fairly long waveforms in some of these modulation schemes. So it's good to have a quality long record length. Being able to synchronize multiple boxes is also a characteristic that's required, especially for the IQ or the polarization methods. Of course, these can be met with the current AWGs today. And then on the analysis side, you can look at the OM 4000 series. And this gives us the capability of again, using an oscilloscope. You may have an oscilloscope already that you can use, so that you don't have to buy a separate analyzer for that portion of it, for the display portion and the calculation portion, whereas you can use a current oscilloscope. So we have some of the best measurement tools available for the coherent optical systems, and we're always working hard to improve this capability even more. And this is something that Tektronix is committed to, as far as providing solutions for our customers in these particular environments.
Find out more at Vicom's website.